Okay, so ladies and gentlemen, we're going to be exploring in the next bunch of lectures a set of material related to a second major type of dynamic modeling, and that type of dynamic modeling is agent-based modeling. We're going to be building on the conceptual foundations that we've laid in the first part of the class, drawing analogies so you can understand what concepts carry over and how they carry over, how they're adapted, and progressively using these tools to explore a larger and larger space in the agent-based modeling area. In contrast to system dynamics modeling, where we're dealing with a very small number of building blocks that at the lowest levels consist of stocks and flows, which move up from there to things like first-order delays, when you have a much larger model, basically what you're talking about is creative combinations of these small building blocks. When you're dealing with agent-based modeling, you're dealing with a wide variety of types of mechanisms and building blocks. You have a much larger vocabulary. Both types of models are computationally universal. Anything you can do in one, you can in principle do in the other. What do I mean by computational universality? Anyone? Computer scientist who's maybe taken machines and algorithms course? When I say that both types of modeling are computationally universal, what do I mean?
Both means to the same end, they just have different kind of ways of doing things.
That's a good summary of it. Andrew? So at a very, very high level, there are different means of accomplishing the same end. And what is that end? Well, when we're talking about computational universality, we're talking about expressing computations. And basically what it means is that anything you can, amongst other things, one implication is anything you can express in one, you can in principle express in the other. And if we think about the notion of computational universality more generally, what we're talking about is that any program we can write in one universal programming language, we can create in another. Okay? Anything we can write in Fortran, we could recode in C++. Or anything we could write in C++, we could recode in Perl. Anything that we could create using a Turing machine, which is the simplest form of representation of computation, we could end up implementing in Snowball or implementing in Scala or vice versa. Now, when we're talking about computational universality, we're not saying it will be nice. I know when I was an undergraduate, I knew someone who was an admirer of a certain programming language called Scheme, which probably not many people here know, but it's a dialect of Lisp. And he loved it. He loved it. And it was just about the time that something called PostScript printers were coming out. You folks know about PostScript? Print language in which we print many documents. They're translated into PostScript, and it's understood by laser printers, all around the world. PostScript. So he thought it was really neat that this printer understood a programming language. So he wrote an interpreter for Scheme on his printer. And basically you could feed it Scheme programs and it would interpret them and perform a calculation for him. So we turned the printer into something that could process things in the programming language Scheme for him, and he used it as a computer. And in general, when we're dealing with one type of programming language, within a broad class, we can take anything we've written there and in principle translate it to another, but it could be really messy. It could be ugly. I mean, I would not want to use the PostScript language to write a Scheme interpreter. It's not my idea of fun. And probably by your standards, my ideas of fun are pretty strange themselves. But it's not a beautiful thing. And indeed, as it will turn out, something that we can program up in one of these simulation languages will often be, so we can program up nicely, will be difficult to express in another. This just happened to be on my screen. Cheryl will recognize this all too well, perhaps. But this is an age-based model of deer movement for mule deer here in Saskatchewan, and it involves progression of a deer along many stages of chronic wasting disease here. It reflects their aging into different age categories. It reflects the fact that that after dying they become a carcass, and this carcass can in fact shed prions, the pathogen, the misfolded proteins responsible for chronic wasting disease. But the deer also have some behaviors associated with them which are seasonally, which change seasonally. In fawning season, in terms, these are the seasonal movements. Here's movement in rut, where the male deer apparently basically go crazy, ignore themselves, and chase after a female deer all the time, and end up in a bad shape, as I understand it from our vet colleagues. So these are different sort of seasons associated with this, and there's behaviors associated with the fawn staying with its mother and with seeking out water and food and so on. This is an age-based model. Translating that into an aggregate system dynamics model on a one-by-one basis would in principle be possible, but it would be hideously complex and ugly, and it would probably be not understandable by human eyes, and it might not even be feasible given the memory limits on today's computers, etc. So we're going to be dealing with a different language, a language which involves a lot more building blocks. We're going to be talking about events. We're going to be talking about state charts for sure. We've already seen a glimpse of that. We're going to be talking about messages to communicate between agents. We're going to be talking about spatial embedding of agents, putting them in even geographical space, and having them reason about the road connectivity or paths in the geography, about the presence of a river that has impact on movement here in Saskatoon. And we're going to be talking about networks and putting the agents into networks, one or more networks, where they can communicate. So there's going to be a lot of building blocks here beyond the stocks and flows that we've used thus far. But a lot of the principles will carry over. A lot of the principles of this idea of an equilibrium, the idea of multiple equilibria, ideas, as it turns out, associated with something as basic as first-order delays. So we're going in a direction that's going to involve a lot of additional components, but you've gotten a lot of the essential ideas: dynamics, nonlinearity, changes in a model, model's behavior that can be radical, associated with tipping points, path dependence and lock-in. All those things will appear here as well. They'll just appear with a different mask on and a different set of trade-offs at a practical level. Okay, so ladies and gentlemen, I'd like to go leave the sphere of deer, if we may, and I'd like to go back to, okay, you don't want to see some of these either. I'd like to go back to that model we built last time, okay? This was the model. It, ladies and gentlemen, it stands before us, okay? Can anyone remind me what was going on in this model? It looks, at first glance, it looks unassuming. We see what appears to be a system dynamics model with what is, in fact, a first-order delay here. Let me go click on this. How do we know this is a first-order delay? What would you look at?
It has one flow, two stocks, and one parameter.
Good, and it's linear, right? So the number of people leaving the stock depends linearly on the number of people in the stock. In short, the flow out, the value of the flow out of the stock is a simple constant times the number of people in the stock. That's associated with what sort of feedback loop? Negative or positive?
Negative.
Negative. Why negative?
This system tends to equilibrium.
Good. It does. It does indeed. And in fact, here the equilibrium towards which it tends is what? Susceptible being 0. If we had an inflow, it would tend towards some sort of balance where what equals what? Inflows equals outflow. Yeah. So that's good. The flow is coming out of this stuff. So we have a negative feedback associated with that first order delay. It's a very simple structure. The larger the number of susceptibles, the more people per unit time are leaving, and therefore it'll tend to draw down the number of susceptibles. That's the feedback associated with it. But this model was not our normal system dynamics model of a stock and flow with a first order delay. What came in addition to this model that made it different?
A basic agent-based model.
Yeah, that's right. There was an agent-based model, and particularly there's this population here, right? And we ran the model. Well, here I should probably remind you of what was in that agent-based model. Here we go. And I argued that this was isomorphic too, that it sort of directly mapped to what was in the system dynamics model. Why is that? What does this map? To what does this correspond in the system dynamics model?
Susceptible state.
Susceptible stock. Yeah, exactly. So, okay, I have too many. Here we are to the susceptible state. So, or stock. How about afflicted? Well, to the afflicted stock. And this transition, in fact, corresponded to what? Yeah, this corresponded to the flow over on the system dynamics side. And in a discussion we're going to come back to in just a minute, we had this rate given by this certain value, affliction hazard. Okay, let's go back to this model. What was the chance per unit time that someone would go from susceptible to afflicted? Okay, that was the number of people going per unit time from here to here. Was each of these people are at risk? Each of them have a certain probability per unit time given by affliction hazard. And so the actual probability per unit time, the hazard rate, the chance per unit time that they're going to go is affliction hazard. And so it was here. And you'll notice there's a little graph here. That graph indicates it's a rate transition, but it also indicates that it's associated with what sort of distribution? Anyone want to hazard a guess?
Normal distribution.
Exponential distribution, indeed. A normal distribution would have several unpleasant properties. It would suggest that negative dwell times are possible here, because a normal distribution has infinite support. It has no limit on the way it goes each way. It gets smaller and smaller, but there's no limit to how broad it is. So a normal distribution associated with this would be an unpleasant prospect. It would suggest that you could spend negative time in the susceptible state, which is non-physical. So this is an exponential distribution, and we're going to talk about that here. Could someone get the door there? I don't want my voice to carry over and disturb the students in the open area, nor in what I hope will be a quieter lounge. Okay, so ladies and gentlemen here, I would argue that we're going to see here a distribution of the amount of time that they spend in the susceptible state before leaving that is described something like this. And this distribution will be proportional to, so the probability of remaining in that state will be given by, if this is a value alpha, affliction hazard, this will be given by minus alpha t. Okay, this is the probability they'll remain in that state. Now, why is that, ladies and gentlemen? Well, the only people who can transition over here are the people who remain in that state. So if we consider the probability that they'll remain in the state, let's just call it P, okay? And we consider, okay, over a small little piece of time, what's the chance that they'll leave? And we ask, what's the corresponding decrease in the amount of time? I would argue that basically what we have is a situation where delta p, the change in probability over some little unit of time, some little delta t, the change in probability here, so maybe this is our little delta t here, and this is the corresponding change in probability from here to here. That delta p, so this is kind of delta p here, and this is delta t here. I would argue that delta p here is going to be proportional here to, anyone want to hazard a guess? The probability that they'll remain there. So if they are there now, okay, then what's the probability they'll stay there over the next little unit of time?
Oh, the hazard rate. Yeah.
Ah, the hazard rate, indeed. So if we consider this hazard rate, alpha, this is a probability per unit time, and we take into account a delta t here, so it's some then it'll be 0.1, 0.01, okay? And the change in probability, is this going to go up or down? Ladies and gentlemen, is this going to be going up or down? Is it going to be negative or positive? So if we consider this little delta t, will p decline or grow? It'll decline. There'll be a negative here. And ladies and gentlemen, the only situation in which we will leave is one if we're already in, or if we're still in this state. So we have a p here, okay? So conditional on being in the state, so that's the probability p, we have this probability of leaving in that little time delta t. If we're not in the state anymore, what's our probability of leaving along here? Zero. We're only going to leave here if we're susceptible. That's why there's a transition out of here, okay? Now, we could divide here that over to the other side, and we're going to have that there. And then, as delta t goes to 0, what is this going to turn into? dp dt equals minus p. Now this is a differential equation, and if you solve it, you will get something proportional to this. Okay, it's actually proportional to that. It'll be some constant up front times this. Okay, some constant, which will actually be related to alpha. Okay. Okay, so ladies and gentlemen, there'll be some constant times it. Okay, so let's think about this. So here we have a situation where this is going to yield p over time, probability of remaining in that state over time equal to, it's going to be proportional to e to the minus alpha t. Okay. That's what we're going to get. That's why this comes out of this situation. But we've seen this before. Where else have we seen this before? Anyone? Where else have we seen it before? Anyone? Where else? We've seen the same sort of distribution before on these very boards. Yeah, so the first order delay, indeed. And I'm going to be more specific about this, ladies and gentlemen. This is actually alpha times that. Just did the integral in my head. So this is equal to that. Instead of putting a constant in front, it's just alpha. Okay. Anyway, yeah, this comes out of a first order delay. This comes out of what we see over here as well. Okay, this is the same formula. So if we run this, I mean, here we're dealing with the number of people. The probability that each of them remains in the state is e to the minus alpha t. So the number of people initially there, which I think is 1,000 here, or 10,000, I think it is, they start with n people, and the number of people remaining after who remain after that amount of time is going to vary with n times e to the minus alpha t as well. Okay, that's what we're going to have as sort of the decrease. Yeah, question.
Shouldn't the first alpha be like P naught or something with the initial population?
Yes, yes. So over there, this would be the initial population times this, and here what we're going to have is it's actually going to be 1.0 times it. So the probability of remaining there, you're right, it's going to be 1.0 times that. Yep, that's correct. So this is the probability at time 0. It's going to be e to the 0. That's going to be 1. So it's probability 1 of remaining there after time 0. And over here, it's going to be n0 times that. Okay? Good call. Appreciate that. So, okay, so ladies and gentlemen, here, if we run this, I would argue that in both cases, if we consider an individual and the probability remaining here, oh gosh, that doesn't look very exponential. It goes more like that. Okay. Here we're going to see this decrease, and in fact, that's what we do see out of a first order delay. So let's go run it. Here we go, and if we watch the value of the stock in the graph, that's exactly what we'll see. Now I want to talk about this a little bit more, and I really want to I want to try to get you to understand a difference here between this hazard rate on the one hand and the probability of remaining in that state. Okay, so let's take a look at this. Let's run it. Oh gosh, this is a big population, right? Okay, it's running along. Okay, and here we are, and already we can see the curvilinear components of this, right? Start from 10,000, go down. This is 10,000 times e to the alpha t, e to the minus alpha t, and as t grows, it becomes smaller and smaller. Okay? Ladies and gentlemen. So that's an illustration here. Each person has a certain transition, the certain probability of remaining there, and if we consider the whole population here, if that certain probability of remaining there. So that's both sides. We have the same basic equations. Now, I'm going to ask you this. Okay, this is the probability that they remain. The probability that they remain after an amount of time t is given by this. Then, ladies and gentlemen, what is the probability that they remain after one time unit?
1 minus the probability that they, what?
Okay, so this is the probability they remain after one time unit, okay? This is the probability that they remain following one time unit. Following t time unit. So what's the probability they remain after one time unit?
E to the power minus alpha.
E to the minus alpha, okay? And what's the probability that they leave within that first time unit? This is the probability they remain. This is P of remaining after one time unit. Okay? From whence did I get that? Where did I get this? From where did I get this?
Just replace T with
Yeah, T is 1. In fact, it would be better to put that. Why is it better? Yeah, but there's actually a deeper reason too. Ladies and gentlemen, this has to be dimensionally consistent. The units. You cannot have e to some power that's not dimensionless. You say, why is that? Does anyone remember how e is defined? If we did a Taylor series expansion of e, if we have e to the minus alpha t, what is that equal to? If I wrote out it as a sum of powers, what is that equal to? Anyone remember? 1 minus alpha t plus minus alpha t squared over 2 factorial plus, now for some of you this won't be familiar, for some it will be. But this is actually how, this is the definition of what this is, okay? And unless this is dimensionless, it's going to be meaningless because you're going to be adding something of one dimension. You know, suppose this were time. Suppose alpha t were dimension time. We added something that's time to something that's time squared, something that's time cubed. It doesn't make any sense. The only way this is going to work is if whatever's here, whatever's in the exponent is dimensionless. Meaning, what do I mean by dimensionless? I used a bad word. It basically, the units cancel. It's unit dimension, meaning it's independent of units. That's what it really means. It doesn't depend on unit system chosen. It's like the fraction of this area up here that's covered by a desk. You could measure it in square feet, and you ask what fraction is covered by that desk? Oh, it's 5%. You could measure it in square meters. What fraction is covered by the desk? 5%. It doesn't matter what units I measure this in. I can measure it in square light years. It's going to be the same 5%. It's dimensionless. It's independent of units. Or you could ask, what fraction of the day do I spend in front of 394? And I could answer you the best. But actually, the actual fraction of it, ladies and gentlemen, would be independent of how I measure time in milliseconds and in hours, in years. I could say, my day is 1/365th of the year long, and of that I spend 1/365 divided by times 2/24, time in front of 394, what have you, and it'll be the same number, right? If you ask what's the fraction of heads I get on a certain number of flips of a coin, it doesn't matter if I count those flips of a coin one by one or in thousands. I'm going to get the same fraction. So that's why probabilities are dimensionless or unit dimension, and basically means it's independent of units. And that's the way the world is. Because it would be terrible. Imagine if the universe crashed if we suddenly changed to metric or something. That would be really bad. So, ladies and gentlemen, this has to be dimensionless, okay? And this has to be dimensionless. All these things have to be dimensionless, because if you add things together that aren't dimensionless, successive powers adding up, you're not going to get something that's meaningful. It's like trying to add a foot to a square foot. You can't do it. You can do it numerically. You have 2 feet plus 2, 2 times 2 is 4 square feet, and you add them together, but it's not going to be meaningful. So anyway, this has to be dimensionless. This has to be dimensionless. So this is kind of representing one time unit times something that's of unit. What are the units associated with alpha? 1 over time, right? This is the dimension, and if it's year, it's 1 over year, and this would be year, right? So they would cancel. That's what we're looking for. In other words, units have to cancel here. So that's why we like to write it out explicitly as times 1. Okay, so that's our probability of remaining there after 1 year. What's our probability of leaving there within 1 year?
1 minus that.
Good, 1 minus that. Now, some of you in the audience maybe feel a little bit uncomfortable with that answer. Maybe you feel from my descriptions that I've misled you. Maybe you feel that the probability of remaining there after a year should be what? Or probability, sorry, this is probability of remaining a year. This is probability of leaving within a year. Probability of leave within a year. Within 1 year. You might think that should be what? Probability of leave within a year. The probability of leaving per year in a year should be what? You might think that it should be alpha. You might think, right? I mean, that's the way it's been kind of described, probability per year of leaving. Well, ladies and gentlemen, I want to explain this quandary to you. Probably leave within a year here, right? And the reason it's not equal to alpha will start to be evident. Now, I'm going to argue it's very close to alpha, and the reason lies right here. If alpha t tends to be small, this thing here, 1 minus this is going to be what? Can anyone tell me? 1 minus this is going to be what? So 1 minus this whole series will be what? Yeah, something very, well, something, yes, very close to actually to 0, right? So excuse me, to alpha t. So if I wanted to say what's 1 minus e to the minus alpha t, well, 1 minus this thing, 1 minus this is 0, and you subtracting off that, it's alpha t, and then subtracting off this, alpha t squared over 2 factorial, etc. So, ladies and gentlemen, I would say if alpha t is small, we're going to get something here that's pretty close to this, because this squared is going to be really small. Suppose alpha t is 0.01. This is going to be 0.01. This is going to be 0.01 squared, right? It's going to be 10 to the minus 4. 0.0001. It's going to be really small, and the rest of these terms are going to be even smaller. And so we might say, well, this is very, very close to, what's up here, to alpha. So if t is 1, it's very close to alpha. But it's not exactly alpha, and why not? Why isn't it exactly alpha? What's off here? What's off about this? Why is this something that's off? Well, let's go over it on this board for equity's sake. So here we go. And I'll take photos of this and post them after class. Okay, here we go. Ladies and gentlemen, I want you to consider a situation where we have here a probability of leaving across a given time unit that's Q. Okay? And I want to tabulate here probability of remaining, probability of remain after that. So if I have a probability of leaving within this amount of time, maybe it's 1 time unit, but within this amount of time of Q, what's my probability of remaining? 1 minus it, right? Good. 1 minus Q. This is the probability of leaving. Prob leaving, right? And the probability of remaining is just 1 minus that, right? Okay, now let's consider a situation where we have, over that entire time, I divide it into half. And in this time, I have a probability Q over 2 of leaving, and this time I have probability Q over 2. What's my probability of leaving over this entire time unit? Okay, it's a good thought. It's a good thought.
Very close.
Okay, well, let's reason mechanically. What's the situation in which I'll stay over this entire time unit? In order to stay, what has to happen? I do not leave in the first time. And what's the probability of not leaving in the first time? 1 minus Q over 2, right? This is the probability of leaving in the first time. Probability of not leaving in the first time is just 1 minus that, right? And then, if I haven't left in the first time, in order to stay the entire time, in order to remain the entire time, what has to happen? I've stayed there half the time so far. I'm at this point. What has to happen for me to remain the entire time?
You just remain the next time.
I have to remain that next time. And what's the probability of that? Q. Okay. So in order for both to apply, and that probability remaining there, given that I've remained to that point, the probability remaining there is independent. So the probability of remaining there, I have to dodge both these bullets, right? I have to not do it here, not do it there. They're independent probabilities, and therefore they multiply by each other. This is 1 minus Q squared here, ladies and gentlemen. That's the probability of me leaving, prob of leaving of leaving in entire time. Okay? Entire time. The point there is this is not Q. You could say it's close to Q, and I wouldn't disagree with you, but it's actually not Q. What's the probability of me remaining there? So this is the probability of me leaving somewhere in that entire time. Sorry? Okay, so let's go through this again. So ladies and gentlemen, in order to, okay, yes, you're okay. I should have done one more, one minus. Good, I'm glad you caught that. So ladies and gentlemen, the probability of leaving in this time is Q over 2. So the probability of remaining during that time is what? 1 minus it. And then you have to remain during the second, so it's squared. So what's the probability? So this is the probability here. This times this, right, is the probability that I will end up not going in the first time, not going in the second time, right? Which is this here. And so what's my probability of leaving during that entire time? This is probability of remaining entire time, right? Entire time. Let's try this again. Okay, so during this initial time, I have a probability Q over 2 of leaving, right? So my probability of remaining during this time is 1 over Q2, right? In order to remain the entire time, I have to remain during the first time and remain during the second time. So I have to remain here the first time, and then I have to remain here the second time. Or for this second time period, what's the probability of me remaining here? 1 minus Q over 2, right? Okay, good. So that's my probability of remaining. If I have remained all through that time, this is the probability of remaining. The remaining time, this is the probability of remaining to that time there. So the probability that I remain for the entire time is what? Multiplication of those, right? I have to remain during the first time, and having done that, I have to remain during the second time. They're two independent events, right? Right? Okay, so the probability that I remain during that second time, I would argue, is given by this thing here, right? The probability that I remain through that entire time, okay? So here we go. And so the probability I remain is this through that entire time. Now let's consider, if we may, this divided up into 3 time segments. And I'm going to divide up each probability. This will be Q over 3, Q over 3, and Q over 3. Okay? Ladies and gentlemen, what's my probability of remaining in the first time? That's exactly right. So 1 minus Q over 3. And similarly for the second time period to remain through there, it's the end of that, and then for the third time period, right? So what's the probability of remaining across all the time periods? Okay, 1 minus Q over 3 to the cubed, right? And in general, can you give me a formula that's divided up into n? What's the probability that I'll remain there over n, for n? Okay, good, good. 1 minus Q over n to the nth power, okay? That's the probability I'll remain across this entire time. Are we okay with that? Again, the only way I'm going to remain that entire time is if I dodge this bullet, and then having dodged that, independently I dodge this one. And the probability of that occurring is the square of the probability of avoiding the first and avoiding the second. Are we okay? Anyone want to raise any concerns about that? Okay, so ladies and gentlemen, I would like to consider, as this goes to infinity, what's the limit of this? So if we have 1 minus q over n to the n, and we consider as n goes to infinity, what does this thing approach? Anyone recognize that? From way back in calculus? Well, it turns out that this is equal to, as n goes to infinity, ladies and gentlemen, we're having this thing to the nth power as n goes to infinity. So n is changing here in the denominator, it's changing here in the numerator, just like it was here, changing in the, sorry, in the exponent, changing in the denominator. What is this going to equal? Hate to disappoint you. You know what this equals? E to the q.
It's that
Yeah. It turns out it's just that over there, but it's ladies and gentlemen. Oh, sorry, e to the minus q. E to the minus q. There's minus here. Yeah. E to the minus. Ladies and gentlemen, if we had one time unit, it's like t equals 1 here, and we consider it more finely and finely, consider it down to the level of seconds, down to the level of microseconds, you have some chance of leaving in that amount of time. And we, in order to stay, you have to stay through each of them. You're going to have this as the limit of it. As you consider there's this hazard rate that can apply at any point. It's not just that you have some probability over the entire time of leaving of p. It's not merely that. Ladies and gentlemen, you're going to have a kick in the can not only every day of the month, not every hour of the day, not every second of that hour, but you're going to be able to consider as finely as possible. I could leave at any point during any sub-interval, but the chance of me leaving within a second is smaller than the chance of me leaving within an hour, right? Chance of leaving within an hour is smaller than the chance of me living across a day. But it's not merely, ladies and gentlemen, a situation where you can break things up and say, well, if you have an entire time and you have a chance of q over 2, leaving the first half, q over 2, in the second half, your probability of leaving over the entire time is q. Turns out that that's not quite the case. It's close mathematically if you're dealing with a small q. So ladies and gentlemen, here what we're dealing with is a situation of, in this hazard rate, I could leave it at any small time. And suppose I have a hazard rate of alpha of, let's say, to pick a nice example, an alpha of 0.12 per year. Okay, so this is 0.12 per year. This is my alpha. Remember, it's a dimensionless quantity over some amount of time. What's my chance of leaving what's the corresponding value if I want to go into months? Well, actually it will be, if I want to translate it into months, it will be 0.12 divided by 12 per month, okay? I'm dealing with a hazard, something where I could leave at any small unit of time. And hazard rates, in contrast to probabilities, I can actually just divide through by the appropriate unit. So this would equal 0.01 per month, okay? I can simply divide through by the appropriate amount. If it were a probability, I couldn't do that. How do I know I couldn't do that? Give me a counterexample. Suppose if this were a probability, I would argue you can't simply divide by in this sort of way. Why not? Well, ladies and gentlemen, think about it. I mean, if I have a 0.2 chance per year, and now I want to consider my chance over a decade, I can't just, over 10 years, I can't just multiply it by 10. Why not? Why wouldn't that give me a valid value?
Look at smaller.
If this were a probability, well, it would be greater than 1, which you can't have for a probability. That's not possible for a probability to be greater than 1. With a hazard rate, could you have a value that's greater than 1? Could you have an alpha that's greater than 1? Yeah, you can. Suppose I had an alpha of 2. Give me some intuition for what that means.
Over some unit of time equal there's a chance.
Okay, so that is true, but that's actually not what defines the 2. Give me another way to express that I have a hazard rate of 2. We actually talked about it. We talked about it in this context. Suppose that my infliction hazard were 2. What's the average amount of time I spend in the susceptible state before leaving? Half a time unit. It's 1 over it. So all it means is I'd leave in general quicker. If it's a probability, I can't have something greater than 1. I mean, the probability over a year that I leave is 0.12. It doesn't make sense. Probability of a decade. But ladies and gentlemen, with a hazard, you can. A hazard rate is different than a probability. A hazard rate, considering, no matter how small you go, there's some little chance that you'll leave during that time. And those chances that you leave earlier mean that the later chances no longer apply. If you leave earlier, it won't apply. So you can't simply sum these probabilities up to get a probability of Q across it. So ladies and gentlemen, here we have a situation where we are going to have we're going to be able to leave at any point from this state or from this stock, and we're going to have the probability of remaining in that stock going down like this, being described by e to the minus alpha t. And that's true regardless of whether we express it with a state here and a transition like this, or we have something like this. The probability someone will remain here and susceptible will go down, it's e to the minus t. And that's what we saw, right? I think I'm going to go to this one. This is a bit smaller, and I'll run it. And what we'll see is a beautiful characterization of an exponential function. There we go. Okay, now we're going to get to 2 other things now, conceptual. I recognize that this stuff is elusive. And ladies and gentlemen, the main thing, I'm not going to hold you responsible for all pieces of this, but what I do want you to realize is that this is not a probability. A hazard is not a probability. And with a hazard, if I'm considering that over the next hour, I have a 0.6 chance of leaving this room, and I would hazard that that's probably the case. If it's 0.6, if my hazard rate is 0.6 over the next hour, what's my hazard rate over the next minute of leaving? If it's indeed memoryless, if it's indeed one of these situations where I have the same chance of leaving per second, per minute, per hour, independent of how long I've spent there. If I have a 0.6 chance of leaving over the next hour, what's my chance of leaving over the next minute? You can give me a formula. You don't have to say the actual number. Well, 0.6 divided by 60. Because a hazard rate is giving not a probability over the entire unit, it's giving a probability density, a chance per unit time. No matter how finely you take it, we could consider, alpha times delta t is the probability that I go in that amount of time, okay? So if I consider 0.6, if my hazard rate is 0.6 per hour, my hazard rate per minute is 0.6 divided by 60, okay? Okay, I hold you responsible for that much. and for understanding that the corresponding element for a first order delay here with a certain fixed hazard rate in an aggregate model over here is at an individual level one of these rate transitions, okay? And that if I have a rate of alpha, that doesn't mean my probability of remaining in that state after time 1 is 1 minus alpha. That's not the case. It's close, but there's no cigar. Okay? It's not exactly that. It's instead my probability of remaining is e to the minus alpha times 1. Okay? Okay. Ladies and gentlemen, which, as we said, is close. It's close because if we consider e to the minus alpha times 1, it's 1 minus alpha t. And if t is 1, it's close to 1 minus alpha, but then you've got these extra terms involved, okay? It's only if alpha is small that they're really close. Okay, ladies and gentlemen, so those are some high-level things to take away. I'll take a picture of this. But now I want to puzzle you with a few more things, if I may. A few more things. Ladies and gentlemen, so one question I would have is this, and it comes back to a question we talked about earlier. And I want to recall our earlier answers for the aggregate model and then talk about them here. Okay, ladies and gentlemen, suppose we were interested in a situation where the affliction hazard is different for men and for women. Okay. Maybe really different. So maybe men are more likely to be afflicted by a factor of 2. And believe me, there are some conditions where that is true. Ladies and gentlemen, how would we alter this model to allow us to track the dynamics in the number of people afflicted over time in a way that reflects those differences between the two sexes?
Would we need to copy,
Yeah.
paste like the model?
Right, the entire model.
Or we can add a parameter.
You could add a parameter, but it's still not, if we add a parameter here, it's not going to allow us to capture the fact that women have different risks than men in terms of leaving. Because remember, one of the assumptions about an aggregate model like this is that everyone in the stock is the same. It doesn't matter how long they've been there, it doesn't matter their types, as long as they're in the stock, they have this certain chance per unit time of leaving, a certain hazard rate. Okay? That's what that's saying. Okay? So ladies and gentlemen, here, if you have remained in that state for a long time or a short time, if you are male or female and you are represented as one of the numbers in that state, you're going to have the same chance per unit time of leaving. Okay? Now, so we could add a parameter to this, but what we're going to need to do is what Jesse said. We would need to conceptually duplicate this model. And I said last time there's some nice ways of doing that, nicer ways, less ugly ways, less hideous ways, at least until you start adding a number of dimensions. If you start to add by income and do it by their country of birth, it's going to start getting messy. You're going to have multiple subscripts here. Ladies and gentlemen, in short though, just to capture a dichotomous sort of possibility, men versus women, we have to duplicate the size of the model, multiply it by 2. Suppose that we wanted to do it for 10 different age categories, each for men and women, and then separately for men and women separately. How many times would we have to copy the model? How many copies of the model would there need to be? 20. 2 men and women times 10 age groups. Okay? Gets very big pretty quick. Now let's think about our agent-based model over here. What would we need to do if we need to distinguish men from women?
Find an age or gender variable.
Okay, good. And in any logic, the way that we would capture that assumption, in fact, communicate this, is with what's called a parameter. just these parameters lived at the level of the model as a whole, the main class. Here, we're going to have the parameter live at the level of the population member. So I'm going to copy this model, and I'm going to create a new version. Ladies and gentlemen, it's a good practice to create multiple versions of things that can be stored separately, ideally in a version control system, at the least as separate files, because you never know when you're going to need to go back to an earlier one. And it can allow you to quickly retrace, when did a certain error first come in? Were my results from that earlier one invalidated because of that, because it still had an error or not? It makes sure that we save our work along the way also. Okay, so ladies and gentlemen, here we have this little model here, and we're going to add a characteristic for the persons. Okay, so we're going to go to palette, and we'll go to the agent palette. We could have gone to the system dynamics palette. There's a lot of things that are in both. Parameters are one of them. But I'm going to go to the agent palette, and I'm going to drag in a parameter. And this parameter, ladies and gentlemen, is going to be called sex. Okay. Now, the full implications of this will play out. Okay? So, ladies and gentlemen, so we have a sex parameter. Now, we're left with a set of uncomfortable choices for how to encode this. And biostatisticians have long lived with uncomfortable choices, settled on ways of working around them. But I'm not comfortable being a biostatistician. So I'm going to go here, and I'm going to add in, ladies and gentlemen, we aspire in computer science to have better ways of characterizing a situation than always being reduced to ones and zeros, despite our reputation. What would you do if this were a Java program and you had to characterize someone's sex? What would be a better way to encode it than 0 and 1? Okay, you could include it as zero, as true or false, and surely women would be the truer sex. But ladies and gentlemen, that also leaves a lot of room for confusion. You show it to someone, you show it to someone who's interested in your model, and they see, oh, this person's sex is true, and naturally they're going to ask, what does that mean? Does that mean they're a man or a woman? It's not evident. It's not transparent. So what will we do in Java to encode that? Well, you can do it with a string. What's the problem with a string? Strings are very flexible, but there's something they're not. And I would say they're not type safe. And what do I mean by that? They're case sensitive, among other things. We could say, oh, we're going to say this person's male, and then we're going to check later, are they male? And we're going to be, maybe we check if they're male with a capital M, but we actually wrote it when we first assigned it with a lowercase m, and it's finicky, and it doesn't check that we've entered a correct value for it. And ladies and gentlemen, I know it may be hard for you in the fullness of your education to appreciate this, when you struggle in these very labs with building programs and getting them to work, working long hours. And the compiler sometimes can seem not a trusted companion, but an enemy at times. I'll tell you, sorry, sorry, wrong type for that, buddy. It sometimes its messages lack the full politeness one would expect and good company. But ladies and gentlemen, compilers and language tools are your friend. Just you have to learn how to treat them well, okay? So ladies and gentlemen, the right way to do this, the right way to have a compiler working for you, not against you, to have your errors spotted when you're building your model, not while it's running in front of the person who commissioned it, is what you want to do is you want to go add in here something that will allow the compiler to know what the proper values are and check that you've given a proper value. And when you want to compare it to a value, you're comparing it to a meaningful value. So we're going to do new, and we're going to do option list. Now this is secretly a name in any logic for something else. Can anyone tell me what it would be called in not Scala, word only so, in Java?
An enumeration.
An enumeration, indeed. Okay. So capital SEX, because it's going to describe a set of all possible sexes, and we're going to have female and male. And I happen to like to put them as capitalized, but conventions between development groups differ in this, software development teams. Capital SEX. So how did I do that? I clicked on the model as a whole and I did option list, capital SEX, female, male. Okay? Are we okay with that? Okay. Ladies and gentlemen, here we go. So now we have sexes defined. That defines sort of the theory of sexes here. There's two sexes. So now we'll go to person, and we'll associate this parameter with a type what? Anyone want to hazard a guess?
Sex.
Sex, indeed, yes. So we associate with a sex, and we'll make its default value female. If we don't specify it anywhere else, everyone will be female. Okay? Great, ladies and gentlemen. How did I do that? In case you missed it, I right-clicked here, new, option list. I defined sex, options, male, female. And then I went to here, person, and I chose sex for the type of the parameter, and I gave it a default value of female. Are we okay with that? Okay, ladies and gentlemen, let's take this a little bit further. Let's go up to the main in the model, and we'll go check out the population. Here's the population, ladies and gentlemen, and you'll notice now each population member is associated with a little formula we can give for how to determine their sex. Okay. Now, turns out we could draw on a lot of different possibilities here. We could even draw their sex from a custom distribution. But for now, I'm going to do something rather simple. Okay? And this is, again, with building blocks that you may use. I'm going to say with probability 0.5, and the way we say this is random true. It'll return true or false with a probability 0.5. It's a Boolean. If it's true, we will make them female, otherwise male. Female, otherwise male. Okay? Now, it may be a good practice to say sex.female to indicate it's female with respect to sex, but by default it knows that. So 50% of people will be female, 50% male here. Where did I go to see that? Well, ladies and gentlemen, person class defines our theory of personhood. Our theory of personness. What it means to be a person in the model. The type of information they maintain about themselves and the processes that govern them. The population characterizes for a particular population. What are the characteristics of that population? So here it's their sex. Okay? Ladies and gentlemen, are we okay with that? Okay, let's let him and her rip. Okay? Oh my gosh. Oh, okay. Mumble. Okay. I hope yours didn't do that. Oh wow. This is a fascinating thing. Okay. Is yours doing that? Okay. That's good. Okay. So carry on, folks. So go ahead and run it, and I want you to go down to the population. Okay. While I sit up here and mumble. Okay. And let's go see here. Here we go. Okay. Mumble. Okay, so ladies and gentlemen, here's our population running. Let's go up to this navigation menu and browse down. And we will see, so how did I do that? Whither did I go? I went up, ladies and gentlemen, to this navigation area here, and I went down to population. And now I can see each person. This person remains a susceptible state, and they are male. This next person, male. Here's a female, male. Here's an afflicted person who is... I saw the affliction for a moment. There we are. Hey, this is an afflicted male, right? Ladies and gentlemen, okay, so we've just distinguished people by their sex. I want to ask you two questions. The first question is, how much... So remember when we talked about adding in age categories and adding in sex to our aggregate model? To our model written in system dynamics at an aggregate level like this. Remember if we even wanted to add sex in, what did that do to the size of the model? Doubled it. We had to Not only that, from a software engineering perspective, we did something that, to me, is outre. I mean, it's really objectionable. We took the whole model and we created a complete copy of it. I mean, to a software engineer, that gives me the heebie-jeebies. Perhaps even more so, the willies. It's disturbing because we're having to make a structural change that's global. We have to modify. It would be an exaggeration, but not much one, to say we have to take everything in the model and change it by copying it. That's very disturbing. That's very disturbing. A small change, it's almost as if, in order to correct your watch, you had to, destroy your apartment building or something. Like one small change destroys a massive amount of everything around you. That's very disturbing to me. Ladies and gentlemen, when we added in a characteristic of a person, how much do we have to change about this model? We added a parameter. Did we have to go duplicate the susceptible stock? No. And in fact, that brings me to my next question. Suppose we wanted this rate to now be dependent upon someone's sex. Would we have to go duplicate this entire thing? No, we could give a little formula here for how it depends on sex. For men, it's this rate. For women, it's that. Let's do that, right? Let's do that. So here we go. And for the rate, going from susceptible to afflicted, if this person's sex equals male, the affliction rate will be twice as high as for females, okay? It'll be the one, maybe we'll just, forgive me, but I'll just hard code it. So for male, it will be 0.02, and otherwise for women, it'll be 0.01. This wouldn't be how I do it for a larger model, hard coding it in this way, but it conveys the point that basically we can have a separate rate here. And ladies and gentlemen, did that force us to go modify the entire model as it stood? Do we have to make copies of this state? No. Each person is keeping track of their own characteristics, and we could use rules for their evolution, which depend on those characteristics without having to modify the whole model. What's going on here? Well, in an aggregate model, remember I told you earlier, and I've used it, I've said it early and I've said it often, that in an aggregate model, we divide up the population, ladies and gentlemen, by state. I said state, but it's actually by characteristics and state. So these are the people that are susceptible, these are the people that are afflicted. And now if we want to consider another characteristic, it forces us to divide the model further, right? Male versus female, for example. So we could have male susceptible, male afflicted, female susceptible, female afflicted. We have to create other stocks, because everyone within the stock is treated equivalently. That's the nature of stocks. They're well mixed. Everyone there is subject to the same affliction hazard, etc. So if we need to keep heterogeneity, we need to distinguish between people here, we need to divide them into different stocks. That's not the case with an ancient population. With an ancient population, each person maintains their own characteristics here. The model is organized in system dynamics. In an aggregate model, it's organized by state and characteristics, and each one keeps track of the data keeps track as the number that have that characteristic. In an agent-based model, the model is organized by individuals, and each individual maintains its own state. And the rules for that individual can make use of the state for that individual, this particular person's state, and have them evolve accordingly. Okay? So that's a big difference. Now, let's take that a wee bit further, if I may, trying to explicate further some of these differences. Okay, ladies and gentlemen, suppose that we wanted to keep track of age categories here, okay? Age categories. We wanted to keep track of 10 age categories associated with this. put aside sex for the moment, 10 age categories. What do we have to do? How many times would we have to, how many copies of the model would we have to have here for the aggregate? 10, right? Okay, for person, what do we have to do if we wanted to keep track of age, and it needs to actually change over time. We want to keep track of age. What do we need to do here? Suppose we want to divide it up into, gosh, it would be 17 age categories, 5-year age categories all the way up to 80 plus. What do we need to do here?
Make an age variable, have that
We could make it a variable, but what else could we, how else could we characterize it? It would be structured. You'd go from one age category to the next.
Add another state chart.
We can add a state chart. So let's do it, ladies and gentlemen, because this will teach you another way of characterizing transitions as well. Often I have multiple goals in mind with a given example. Okay, ladies and gentlemen, this will be age state chart. Okay, and this isn't the most elegant way to do age. We'll see soon enough that you can keep track of continuous age, which may cause some of you to pause. And rightly it should. Continuous age. We'll get to that. We could have continuous incomes. We'll get to that. Okay, so here's age 0 to 4 and age, and we're not going to do all 5 to 9. We're not going to do all 17, but we'll do 3. Here. Okay, here's age 10 to 14, and I think you get the drift. Okay, ladies and gentlemen, I'm going to draw transitions between these. And you notice that these transitions by default show a different symbol than that. And that's a symbol they're not associated with an exponential distribution. This clock suggests they're associated with something that's more deterministic than that. After all, the notion, this notion of the watchmaker suggested a certain measure of kind of determinism here. So, ladies and gentlemen, what would be associated with this? How many years to go from here to here? Well, actually 5, because it's 0 to the end of 4. It's a good call. I could understand why you might think 4. Okay, 5 through 9, you would leave here after how many years? 5 years. 5 years, ladies and gentlemen. Okay, now we have people leaving after exactly that amount of time. How could we do that in an aggregated model? Have them leave after exactly that amount of time? Mumble. It's not easy, ladies and gentlemen. In fact, I argued that the only way you can approximate that is by stringing together many, many first-order delays in a row. And you get something approaching something that's going to leave after exactly the amount of time from the whole string. But it's a very awkward way. You have to modify the structure of the model just to capture a different distribution of leaving. Here we leave after exactly that amount of time. Now, I'd like to show this, and as is so often the case, time is short. Ladies and gentlemen, I picked this individual, and I suspect some in the audience may have picked other presentations. And if so, you're on your own. I know some of you may have the forklift, and I'm not going to even try to get its tongs to change color. But ladies and gentlemen, we're going to go have this person's, it looks like their noggin, change color here, okay? It has a certain color for them, and we're going to, it looks like their hair, actually. So ladies and gentlemen, I'd like you to go from the palette, add into this model a color variable. Okay? Color variable. And the type of this will be color, but it will be the class color. How do I spell that?
Capital C color.
Yes. And by which spelling convention?
Just O.
Is it you are? No, it's just O. ladies and gentlemen, the class was dictated by the conventions of the American Imperium. Okay, this is dictated by Oracle, before it by Sun, and we can't do much about it except complain. Okay, okay, the initial value of it will be black. Okay, and then age 0 to 4, we will have color. This dot color be set equal to red. So we're going to put in an entry action here. When you come into this state, we're going to assign a value to color. When we come into this state, we will assign it to magenta. Don't worry if you don't know what that was. I lived 47 years before knowing what it is too. And then one of my students introduced me to it. Actually, a student, yeah, one of my boot camps. Okay, and this will be green, okay? Okay. You can put in fuchsia as well, and that will teach me something. Okay, color equal green, okay? Now, finally, let's go up to our little person, but actually, let's do it through this on the left. Here's this model. We're going to go down to person, and I expanded it to see presentation and patient. Patient is a name for this little fellow. And I'd like you to go here, and it looks like this is depicting his or her head color, but I'd like to set the fill color here to be dynamic. You do that. How did I get there? I went here. You may have to expand it. I went and expanded person. I went to presentation, went to patient, and I went down to this. And again, the forklifts among you will have to fight on their own. And then I went down to fill color, and I did this dot color, okay? Color with an O-U-R-A. Hey, okay, it doesn't always do a nice autocomplete, so I'll just do it for it. When I was young, we didn't have autocomplete. And yes, we didn't program all in ones and zeros. Okay, this dot color. So how did I do that? I went up to this particular place, went down to appearance. You may have to expand it. Went to fill color. I click this, and then I type that in. Are we ready to run it? Ready or not?
Yes.
Yeah.
Here we come. Okay, so let's run it. Okay, and here we go. Okay, now all those people seem to have what color hair right now?
Black.
Okay. Okay. Oh. Okay. Okay. That's an interesting thing. I would have expected them. So what is going on here? They age really quick, but then they would end up with green hair, which is not often associated with elderly individuals. But
Can you just check the state chart and see where they're sitting at?
they seem to have black hair, which would suggest that perhaps, yes, I could. Okay, so a hypothesis. Okay, ladies and gentlemen, when something goes wrong, we have to build hypotheses. So my hypothesis is they're only getting the first value of this. What could be done to check that hypothesis? Let's make the hair color yellow. Shall we not? Okay, let's see now if they all end up with yellow hair. What in Chinese is called huang mao. Okay, here they're all have huang mao. They're all young individuals, it looks like, with yellow hair still. So, ladies and gentlemen, somehow it's only getting our initial value. Okay, that is peculiar. Okay, so yes.
It's because you're using a variable.
Yes.
The state isn't the actual class state is not being updated.
Yes, okay.
It's not actually updating.
Yeah, but it should when it changes states, I would think. But
You would hope, but I've run into this issue before.
okay.
So that might be one of the reasons it's happening. Maybe not.
Yeah, no, I have no better hypothesis right now. Okay, ladies and gentlemen, it's peculiar. I would have thought that would update just fine, but I guess we're going to need to put in place some mechanism to make them update periodically then. Right, Scott?
Well, there's one way to do it. I mean,
Okay, speak
I
on.
do it a little different way, but,
How would you do it?
I directly manipulate the color of the objects.
Sure, Sure. Okay.
That's what I did.
Sure. Set color.
Mine's working.
Same.
Well, I didn't mind color without a U, and mine's working.
Or American imperialism, huh?
Yeah. Okay. So my comment on that is mumble. Okay. Well, a mystery for us collectively because
Well, you're running Windows.
some are not. Some.
Did you set your timeouts?
5 years.
That was another concern.
5 years. Okay. Okay, ladies and gentlemen. Normally, I've done this many times before. It should work. Let me just introduce you to an event. I'll make a cyclic event with a certain timeout of 1 year, and let me just see if that actually changes the situation at all. I suspect it will not, but I'm very puzzled because I have literally done this sort of thing many times before. And once again, they are not, that color is not being updated, okay? So very interesting, this dot on change. Okay, and I think we may have to resolve this via email. Nope, doesn't work, okay?
So it's not an issue with the.
And maybe AnyLogic version, the new AnyLogic version.
I'm using 734 right now, and I don't have this problem generally.
Okay.
Can you look at the state chart? When you
Yep.
run it?
Yep.
Because I just ran it, and the second state chart isn't showing up in the agents.
No, that would
It has something to do with that.
okay. That would explain a lot.
As for why it's not showing up, I don't know.
Okay. Okay. Oh my gosh.
Interesting. Check each state chart, the actual entry state.
Yeah. 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 Yeah.
It's visible. It's not
Yeah,
ignored.
yeah. Okay, watch this. Watch this. I am going to cut it,
And paste it.
and I'm going to paste it in. Okay, and I'll frob the location a bit. Okay, here we go.
That should not be happening.
No, it should not. Okay, mumble. It's using. I wonder if it's because of the build problem I had. Just recently, remember it exhibited builds challenges. Here, let's go open it again. Open this, and how many people's is working? How many people's are working? Okay, how many people's are not working in the same way as your professors? Okay. Well, either one, you're in fine company. For those who's is working, oh look here, it's working fine. I just reopened it, and now we no longer have population of Huang Mao. We have them change the color, and indeed they are recommended by 2 state charts and not 1, and they are transitioning in a fixed time between these. Okay, so ladies and gentlemen, if you get a builder like that where it says it can't build it, close the model and open it again. And it sounds like that's the answer. Otherwise, it's going to be ignoring changes to the model. So that's all for now. I'm going to release a little take-home exercise and then the assignment by the end of the weekend. Thank you very much. Is that interesting?
Well, I mean, basically, it was running the job code. It was. It
Correct.
stopped actually writing the job code in the background.
Correct.
Yeah.